Good morning, everyone, and I would like to thank the organizers for providing me this opportunity. Today I will talk about our recent work, the density correlation and current fluctuation in hard dot case, in collaboration with Professor Anupam Kundu and Seema. So here I will report the results of this ongoing work. So some results we still need to understand, and some are still remaining to compute. The description of hard dots that has been described by Mrinal in the last day. I will not go to the details. Maybe I can recapitulate in first 2 or 3 minutes. So I start with a generic non-integrable system. So what we know that any generic classical Hamiltonian system that's starting from any generic initial condition that eventually evolves, and after a long time it thermalizes to the Gibbs state, in the sense that all the macroscopic observables, they can be well described in the Gibbs ensemble. And this Gibbs state can be characterized by a few conserved densities of the system, like the mass, momentum, or the energy, and like that. However, there exists some systems where there are extensive number of local conservation laws, which basically restrict the motion of the system in the phase space, and the system fails to thermalize to the Gibbs state. And this kind of system are commonly known as the integrable system, which are believed to be thermalized to the generalized Gibbs state upon this coarse graining. And here, there is a nice schematic description that I took from the lecture notes of Benjamin Doyon that basically says the schematic description of the integrable and non-integrable system. So, in the context of classical integrable models, so these are the few examples of in the context of classical integrable models which has been studied from the past decade. And in this today's presentation, I will mostly discuss about the hard dot system. So, what we consider this kind of n hard dots, each of length a and of unit mass, let's say, that evolving in a one-dimensional infinite line. And this constraint basically says that the two hard dots cannot come closer to this distance a. Now, these hard dots, they eventually move with a ballistic motion in between two successive collisions. And when they come together, they kind of collide, and their momenta kind of exchange. So as their momenta only exchange in this kind of system, so all the moments of the momenta kind of concept. So this is the concept quantities for different values of alpha. Now, this hard dot system has been studied extensively using the hydrodynamics approach and also the microscopic approach. So there is a recent study by Mrinal and Anupam that Mrinal described in the last day. So using what they have discussed there, that using the microscopic approach, they studied the time evolution of the conserved densities of this hard dot system, starting from any initial non-equilibrium condition. And their microscopic approach basically in the thermodynamic limit, it not only getting reduced to the Euler solution, but also it captures the this kind of Navier-Stokes correction and goes beyond the Euler solution. So this I will not describe. So what we want to study here. So we will also discuss this collection of hard dot system, the time evolution of this kind of collection of hard dot system using microscopic approach. And we are interested about this two-point density correlation function and the joint probability density distribution. So that we will compute here, and we will study this behavior in the large n limit, and finally we will go to the integrated current in this system and compute its distribution and fluctuation. So this is the plan of this talk. So before going to our results, we just recall the dynamics of the hard dots. So let's say these are two hard dots, black and this red one, in some time, let's say initially at time t equal to 0. And when they come together, they are kind of collide. And due to the collision, their momenta kind of exchange. So this one gets the moment of this one, and this one gets the moment of this one. And ultimately, this red one, it goes like that, and the black one, it goes like that. So suppose if they do not interact, so then the black one follows this dotted part, and the red one follows this dotted part. So what we see here, that upon a collision, this hard dot, it basically jumps over a distance a. And there is a shift that in addition to the drift velocity. So this shift also we can see if we plot the trajectories of the hard dot. So suppose if we label one particular hard dot, this red dashed one, and if it does not collide with the other dot, it follows this path. But as it collides with the other rods, in final it goes like here. So we see that there is some kind of extra displacement of the hard dots in addition to the displacement due to the drift velocity, and this additional displacement comes because they collide with the other hard dots and they jumps over the distance. Okay, so now we go that how we discuss the time evolution. So for the time evolution, we basically discuss first we map the hard dots to the hard point particles. So there is a nice transformation. So what we do, suppose there are n hard dots between 0 to L this length, and the transformation is like that. We remove all the inaccessible spaces between these hard dots such that it reduces to the point particle picture. So there are n point particles between 0 to L minus Na, this length, and the transformation is like that. So here small x and small v are the phase space for this point particle, and the capital X, capital V are the phase space for this rod one. And this kind of transformation has been introduced first by Lebois, Parkhurst, and Saikas in 1969. So what we do, first start with the hard dot configuration. Initially, we map it to the hard point particle configuration. Then we time evolve, and from this configuration, again we map to the hard dot configuration. So this is the general thing that we basically do to study the time evolution of hard dot system. Okay. So with this basic background idea, we just focus on our results. So first we compute the 2-point density correlation function and the joint probability density. So what it means that suppose we consider the initial configuration of the hard dots and then we time evolve the system, and this is the any typical configuration at any arbitrary time t. This is the ith hard dot, this is the jth hard dot, say. So what we want to compute here, that the joint density distribution, that the ith hard dot be at x1 at time t equal to at time t, and the jth hard dot be at x2. So this joint density distribution that we want to compute, and also we want to found that how these densities are kind of correlated. So using microscopic computation, we obtain the exact expression here. So this P is basically the probability that a hard dot from initially time t equal to 0, it evolved to that configuration at some time t. And we can find the exact expression in terms of this P and Q. And we also compare it with the exact results for this initial profile for 10 hard dots. This is the joint distribution, and this is the 2-point density correlations. The solid lines are from the exact expression, which matches well with the numerical simulation. So then we try to find this density correlation in the large n limits. So why we are focusing on large n? Because yesterday Minal said that for this kind of dominal initial configuration, so for this spatial dot and background dot, they basically studied the density profile using microscopic and also as well as in the Euler case. And they obtained that this Euler solution, this matches well with the numerical simulation except this jump. So here is in the jump region, there is a kind of mismatch. So later they obtained this kind of expression that is basically the density in the large but finite n limit and with small a. So we verified that this expression in the large n limit, it goes well with the simulation case. So we want now for our case, we want to follow the same criteria. We want to compute this exact expression in the large n limit, and this is the exact expression in the large n limit. But here we need to compare with the dominant initial condition that is still remaining for our case. We still need to compute. And then we go to the next part. We try to find the integrated current. So integrated current basically quantifies the net flux of the particles across a given point over some time interval. And we, to understand it better, we start with a very simple example, the one-sided diffusion problem. We considered the stochastically evolving particles initially at the left of the origin with some uniform density, let's say rho. And then once the initial, this constant is released, all the particles are allowed to move on the full line. So one of the natural quantity of the interest will be that what is the net integrated current up to time t through the origin. And it's clear that this net integrated current is basically the number of particles which will be right to the origin at time t, originated from the left of the origin at time t equal to 0. And thus we can represent this qt is basically the difference between this nt and n of 0. Now we want to compute this for the hard dot system. So we consider the same kind of initial condition. This is at time t equal to 0, and then we time evolve. And after the time evolution, these hard dots can go anywhere on the infinite line. So it's kind of a free expansion. And here, as we said, that this integrated current is basically the number of rods which will be right to the origin at time t, originated from the left. So it's kind of a random number. And this randomness comes from the stochastic trajectories of these hard dots after time t and also from the initial configurations. So here one can ask that what will be the distribution of this integrated current and also how they fluctuate. So first we compute the distribution. So what it means that starting from this initial configuration, the probability of how many dots are right to the origin at time t, this at time t. And we find the exact expression is basically there are j number of rods right to the origin at time t, and we compare it with the numerical simulation for 20 hard dots. So its solid lines are from the exact analytical expression, which matches well with the numerical simulation. And then for the current fluctuation, we need to compute this first and second moment. So here for the first moment, for this initial configuration, n0 is 0 because there is no rods right to the origin at time t. We only need to compute this nt average, which is basically the average number of particles which will be right to the origin. So this is the exact expression that we compare it with the numerical simulation. And in a similar way, we computed for the second moment, this nt square average. This is the exact, and we compare it with the numerical simulation. So this one is the variance of the rods which will be right to the origin at time t. And this n0 square average will be again vanish, and we need to focus on this term, this nt n0 average. So it basically says that for this, we need to compute the joint distribution that the ith hard dot be at time t equal to 0 be at x1, and the jth hard dot b at time t it is at x2. So this joint distribution, we have an explicit analytical expression for that, which is kind of a big expression we cannot put here. And also we need to understand the result, and also we need to compare with the numerical simulation. So this is the kind of the work that is still remaining now. So this is the summary of my today's work. And I will just conclude with one remark that, but I said that the trajectories of the hard dots, so there is some kind of extra displacement in addition to the displacement of their velocity. So if we take one particular simple example, that suppose in the hard dot system, if we tag one hard dot with some particular velocity, let's say v naught, and we follow its trajectory. So this kind of tagged dot system is called the tracer dot system. And what happens is that the fluctuation in the number of jumps due to the collision, it fluctuates from one configuration to the another. And this basically, for this tracer dot system, it basically gives rise to the spreading of the distribution of the position. And for this kind of single hard dot, this distribution has been described by Mrinal. And when there are two this kind of tracer dots, so the dynamics of this kind of two tracer dots, it will be discussed by Seema tomorrow. And also she will discuss that how one tracer dot is correlated with the another one in this kind of system. So please follow that. And thank you.
In your plot that you have where these lines are going and colliding, yeah, this one?
Yeah.
So there's the dashed line kind of going at a steep angle, but it almost looks like there's like a...
No, basically that suppose these are the trajectories of different hard dots.
Yes, but if you look at like the collisions, it seems like there's almost a shallower line going. It looks like it could be like or something.
No, basically here we just label one particular hard dot.
Yes,
and
yes,
then
like,
we see that how the trajectories are for that particular dot with some label. Let's say that we color one particular dot initially, let's say some red one, and just follow that how this red one travels, I mean, after each of the collision.
Yes, yes. I just mean the collisions, it almost looks like there's another kind of emergent line moving across.
That is because they're kind of due to one particular collision, there's some kind of a jump for each of the cases. And this dot initially is like that, then it jumps like here. Again, so, after the collision, it jumps.
Can I somehow back out like a speed of sound?
Sorry?
Can I somehow back out like a speed of sound in this? Like
the
if you
speed,
give a perturbation that travels through?
Yes, but in addition to their speed, let's say the speed is v naught. So in addition to the speed, there is some kind of extra displacement that comes that how many rods it collides with. So that is kind of that displaced in everywhere.
Okay, thank you.
Okay, any other questions? If not, let's thank Indranil.
Thank you.